Okay, so more than 20 plus attendees. So let's begin. So again, thanks for joining us for this part two of the CopPhil Land Cover Monitoring Training Series. So we're now at the practical session. And this practical builds directly from the part one land cover fundamentals, which introduced us to the fundamental concepts related to land cover mapping using Earth observation. And today, we'll guide you through the process of generating land cover maps using Copernicus satellite data. So we'll have Sentinel-1, Sentinel-2, and also show you the CopPhil land cover classification chain. And here, um, we have first a few housekeeping rules. So I'm admitting everyone again. So for our participants,
Ay, sa
we
yung
ask
anchor pala.
everyone to turn your microphones off for like the recording and just also the video off. But of course, if you have questions, feel free to drop them over the chat box, and we'll have here Etienne and Marion to answer your questions. So your participation is very welcome. We also would like to get your feel on things. So, like for example, we're gonna be having this poll. Um, this. So, uh, whenever Etienne asks a question, so feel free to vote in if you understood things. So just vote in yes, your responses will be very valuable for us. Um, and then yeah. Also, if you can also rename your screen name, so just indicate your name, also your affiliation, just so we can track uh, your affiliation. Also, if you ask questions, then we know where you're coming from. And then again, we're recording right now, and you have a view of this recording and all the other training materials in the training platform later. Then to begin, we'll shortly have this introduction to CopPhil from the EU ambassador to the Philippines. So have a few moments.
Good day to everyone. As the European Union Ambassador to the Philippines, I am very honored to represent a European Union made of 27 European countries with a shared commitment to peace, prosperity and sustainability and democracy. The European Union is not just a political and economic union. It is much more. It is a global partner which values cooperation, inclusivity, human rights. Here in the Philippines, the European Union has been a reliable and consistent partner for over 6 decades. We support a very wide range of initiatives, from promoting peace, good governance, human rights, to enhancing common security in a complex geopolitical context, advancing digital innovation, trade, disaster risk reduction, green economy, and much more. This long-standing partnership reflects our deep commitment to working hand in hand with the Philippines in building a more sustainable, resilient, and inclusive future where no one is left behind. In the Philippines, a country especially prone to hazards and the consequences of climate change, this means supporting initiatives which create real opportunities for communities, foster innovation, build resilience in face of these global challenges. And in this context, the Philippines stands to benefit immensely from the integration of Earth observation technologies. This will strengthen the country's capacity to address climate and hazard-related vulnerabilities and will support biodiversity conservation. I am very proud, therefore, to introduce CopPhil. CopPhil is a unique flagship initiative of the European Union Global Gateway Strategy. It is managed by our team here at the European Union delegation, and it is implemented by the European Space Agency in partnership with the Philippine Space Agency and the Philippine Department of Science and Technology. CopPhil promotes the use of free and open satellite data from Copernicus, the EU space program's Earth observation component, through activities including the establishment of an IT infrastructure and Copernicus mirror site for accessing and processing Copernicus satellite data on biodiversity, on forest management, on agriculture, for example. This transfer of data is reinforced by the CopPhil training program, through which we are very excited to cooperate with institutions across the Philippines. These courses build a shared understanding of value and practical applications of Copernicus satellite data. Together, through CopPhil, we are advancing a partnership which empowers the Philippines to become a central hub for Earth observation in Southeast Asia and supporting its path towards a more sustainable and resilient future. I would like to sincerely thank all of you, the participants, as well as our partners and stakeholders who have made this training possible. Your dedication, your enthusiasm are the foundation of the CopPhil success, which is a very important joint initiative together with our Philippines counterparts. Let's remember that our progress relies on ongoing cooperation, shared learning, mutual support. The challenges in front of us are complex, this we are very aware, but it is united in purpose that we can build lasting solutions. Thank you very much.
So that's an introduction to CopPhil. So again, so this is the national capacity building project for the Philippines. And why are we doing this? So especially for the topic of the day, which is land cover, is that so the Philippines, we have these very rich ecosystems and we're very exposed to rapid land use changes. And with this increasing pressure, we really need to monitor and manage our landscapes. And one method to do this is to have the Earth observation to understand the changes over time. And we want this to make the Earth observation data very useful too. That's why we have the CopPhil project. And for this, we really need local capacity to process, analyze, and apply these processes. And this is also why we have this session. So, and we have this whole CopPhil pilot services training. So we began with an introduction to CopPhil. We had the part one courses, the theoretical courses, which discussed all the concepts related to the EO services. So we have three main EO services. We have the ground motion monitoring service, we have the land cover forest crop monitoring service, and then the benthic habitat service. And then from this part two, we'll have a part three session over August to have the application courses wherein we'll have the more in-depth training on how to use the CopPhil service themselves. And this, we have this CopPhil training program overview. We had these courses overall, and we're happy to have you here and also from the previous courses. And then we have the last batch of application courses soon, and also leading to this final event over the first week of August, leading to the Philippine Space Week. So we'll see you there. And then for every material, you can find them over the CopPhil Digital Campus. So for all those courses, all the recordings, they can be found here. And we also encourage you to have a look in this, please register and also access and learn from our courses here. So for that, you just need to create an account and then browse the courses and enroll on them. And this is also the way to earn your CopPhil training certificates. So for every course and every training, you can generate your certificate of attendance. And to do that, you just learn the course and complete some assessment forms. So it's just a few questions there, and then you have your uh, training certificate automatically generated. So the same for the certificate of participation, and you find further instructions later on after completing the part 1, 2, and 3 of every course. So, but right now we're still at the part 2. So yeah, right now we'll be having again the land cover monitoring practicals, and by the end of the day, you'll be able to work with Earth observation data sets from the Copernicus mission. So Sentinel-1, Sentinel-2, also working with some digital elevation models. And then there's going to be this run through to create and manage your own reference data sets for land classification, and then also really understand the workflow for the CopPhil Land Cover service, and also interpret the results. And with that, I'm happy to hand over to our trainers. So we have Etienne and Marion from CLS. So let's get started. And hi, Etienne. Hi, Marion.
Thank you, Carla, for the introduction. Hello, everyone. I'm Etienne Ducasse. I'm a research engineer here in CLS in France. So good morning or good afternoon for you, I would say. I'm joined by Marion. She will present herself.
Hello, good afternoon, everyone. So I am Marion, so you may know me by now. I will just be assisting Etienne in this training, so he will be the main presenter. So I might be chatting over in the conversation. And so as Carla said, we will use this conversation to add some polls and to ask you to answer it. So for the one who have already worked with Mentimeter with the forest session, it's a bit similar. So we will maybe ask for the first question soon, just to make sure that you see the process, and it will help us to know if everything is clear and if we can go to the next steps. And also do not hesitate to ask questions in the chat, and I will be then asking Etienne to answer them. Or you can also just raise your hand and ask your question. So this is we like to have this session as interactive as possible, although we know that it's difficult when we are all in Visio and in not in the same room, but let's try to do our best, and just do not hesitate to raise your hand, ask your questions, or ping us. Yes, thank you. And I'll let it to Etienne now.
Yes, thank you, Marion. I just put the requirements in the chat. So just as a reminder, there is some files to download, and you should have a Google account to access the Google Colab notebook, and we will be using QGIS. So I hope everything is okay. Maybe Carla, you can put create a little poll, or yes or no, if the requirements are set for everyone. It will be a training to test the system for all of us.
Carla will be adding a poll soon.
Yeah.
And you can try to answer the poll, saying like if everything was okay for you and you install and you have everything, or if you need some, you still need to download or to install some of the software. Carla, yes. Okay, here it is. So you can find it in the conversation now. So you have to answer. Do you have the requirement ready? Yes or no? Or download it now and submit your vote.
While everyone is answering, I will just present a little bit about the plan for today. I'm sorry, I will let this as not in the presenter mode because we will switch to QGIS, so it will be a little bit more simpler this way. So after the introduction we just had, we will dig into the Earth observation datasets. Just after we download the dataset, how everything is organized for each main sensors used for the land cover service. So the Sentinel-2 sensor, which is the optical sensor, and for the Sentinel-1, which is the radar sensor. And then we will do some work on create indices, for example, using QGIS. One another important part is the reference dataset that is used both for training and for validating the chain. So here in this part, I will give you some tips to create accurate reference datasets. Then we'll do a little break, and we'll come back and talk a little bit more about the land cover chain, how it works, a little bit digging into the time series, because it's not only one image, but it's a series of images that are being used in order to do the classification. And at the end of this exercise, we'll do a little classification using random forests. And then we'll present you an example of launching the land cover service. And then we'll look a little bit into the products of the chain. So I hope everyone is ready. I think that some people are still downloading, and that most people have everything ready, if I'm correct. So maybe we can start by handling the observation datasets part. A quick word of introduction about the Sentinel-2 dataset. So everything you can download it. All data is cut into tiles based on the military grade reference system. So with a label corresponding to each tile. So, for example, for the Quezon city and part of this Luzon area, the Bay of Manila, it's 2 tiles, 51 PTS and 50 PRB. So when you want to download it, you need these tile names very often, and everything is cut this way. Also, something that is good to know, there is 2 levels that are ready to use by end users for Sentinel-2 data. The first level is 1C level, which corresponds to reflect top of the atmosphere reflectance, meaning that there is no atmospheric correction. So it can induce some effects due to water vapor, for example, or some light artifacts as well. And it can be used, for example, for indices, because it's not very, how can I say, problematic. But very often we prefer to use the level 2A dataset, which consists into bottom of atmosphere reflectance values. So everything is corrected from the atmospheric effects. And the idea is that everything can be compared from one sense to another, because as the atmosphere is pretty much removed with all scattering interactions, you can compare in time whether the value of reflectance And so it's more practical for us in terms of use for land cover chain that use the time series. So it's much more consistent to use level 2A data. So yeah, we are going here. You can see on the right 2 examples of L1C and L2A. And what we are going to do, it's first we are going to look at the folder, the EO image folder that you just downloaded. So here it's the EO image. And then we will look at a little bit about the data inside this folder. So we are going to the Sentinel-2 folder inside the EO image. And here we have several files. So we have a Sentinel-2 tiles file, which corresponds to the military grid system that I presented you just earlier in geo package format. So it's same as shapefile. You just open QGIS and drag in it, and you can see all the Sentinel-2 tiles covering the Philippines. And then we have 2 images. The first folder corresponds to the L1C level image, and the second to the L2A level image. So let's see the L1C first. And you have several folders. The first one corresponds to the information of geometric information from the acquisition, meaning the angle of view of the sensor, the geometric information about this. In Granule, we have the data, and we'll look at it just after. And then we have HTML, which corresponds to a folder with some info at HTML format. It's for sharing. It's the info that are used for the Copernicus browser, for example, just in order to have the quick look. And we have a preview here, if you want to see, just without looking at all the very heavy data set. So we'll look at the image by clicking on Granule L1C. And we have, again, several folders. Auxiliary data are some data corresponding to metadata corresponding to the geometric information. And QE data are some metadata as well concerning the pre-processing that has been done before level 1C. And image data correspond to the data folder. That's the one that interests us for now. And you can see all images here. So each band, each spectral band. So we have 12 bands on 13 bands, sorry, on Sentinel-2 data. And we have another file which corresponds to TCL correspond to true color, meaning that, for example, to look at this data in the RGB color, it's much more quick to use this one because it's the combination of the 3 RGB band. So namely the band 4 for the red, the band 3 for the green, and the band 2 for the blue. So first thing, we're gonna open the true color. So I will let you open QGIS. And yeah, as Carla reminds, don't hesitate to comment. If you want to post some of your results in the chat, you're welcome as well. We can comment about this. Oh yeah.
So now you should be opening QGIS. just raise your hand if you have some difficulties, maybe. Or if it's okay.
And you just need to select your true color file and then drag and drop it. And now it should load and appears in some time. So just for you to know, we have several spatial resolution for these bands. We have the first 6 bands which are at 10-meter resolution. We have 2 bands at 20 resolution, and the other band are the thermic band, which are at the band 12, which are at the 60-meter resolution. So yeah, you have the L1C image that has been loaded, and so we have our first image in QGIS. Now let's look at the Sentinel, the L2A level, processing level. So we come back to the Earth observation image Sentinel-2 folder. And then we can look at the L2A image right now. So same thing as before, we have the same first folders, data strip, granule, and HTML. We look at granule, and then it is stored a little bit differently because in image data, we have 3 new folders where everything is stored at different spatial resolution. We have at 10-meter resolution, as I said before, sorry, I said 6, but it's 7 bands. No, it's not 6. Here you have 6 bands, but there is 2 corresponding to the atmospheric correction. So, for example, we have the aerosols. If you are interested to look at the pollution, for example, or some information about marine, about aerosols, you have something that can be looked at here. And another byproduct of the atmospheric correction, it's the water vapor product, which is here. And both of them are side products from the atmospheric correction and has been used in order to create the L2A reflectance data. And here you have at 10-meter resolution the 4 bands, band 2, 4, 3, and 8 at 10 meter. So for red, green, blue, and near infrared bands. At 20-meter resolution, you have these same bands with some other bands, B1, B7, 8, 11, and 12, which are only at 20-meter resolution. Plus, you will have a new file, which is a SCL file, which is quite important actually because it's the classification of clouds that can be used after for masking the clouds in order to do some processes. But we'll look into that just after.
Etienne, there's a comment, maybe, or a question. I don't know if it's both. Saying that there's only
pre-file in RTNM.
No, you should have more.
Oh, yeah, you should have more. Maybe it's a download problem. Yeah, does other people have the same issue?
But you will not use it in the demonstration, will you?
Yeah. In the demonstration, we will not use it. We will only use the 20-meter resolution because it's a little bit more quicker as a demo. Okay. And as we don't dig into the data very precisely, So we will stick at 20-meter resolution. So I invite you to use the true color file, which is located in the R20 meter folder, and then we will drag and drop it to compare to the L1A file that we just loaded before. So yeah, we'll just come back to that later. So so as you can see, when we look at we can see 7 in the Google Drive. Yeah, it should be all 7 files. So you can see the difference between the non-corrected and the atmospheric corrected. And you can see also some differences in slopes in particular. So I invite you to just switch on and off these 2 images, and to, for example, as the atmospheric correction includes some scattering correction due to the relief. So second term shadow like this one here, I will zoom a little bit. You know, you see these slopes here are a little bit corrected to have a more homogeneous reflectance values over the surfaces. So it will remove some artifacts due to the slope and to and it applies the terrain correction, basically. So I invite you to look into this, and then we see still that we have some clouds. So some exercise we're gonna do. It's we will use the SCL file that is located in the R20M folder, and that I would like you to do using this information. So it's, I will increase this a little bit. Using this information is that only visualize the vegetation, non-vegetation, and the water by changing the symbology. So I will just show you a little bit how to proceed. So we load the SCL layer. So it's a scene classification. So meaning that there is a first classification used for the atmospheric correction, and that allows to detect land areas, to clouds, to shadows, and to defective pixels. SCL mean scene classification layer. And so I will just let you dig a little bit about the symbology. When you're going to right-click into on the layer, you're going to properties and go to single band pseudocolor. No, to paletted unique value and classify. So paletted unique value in symbology. And so using this, I will let you play a little bit with this, knowing that only usable pixels are labeled between 4 and 6 to just set it as transparent, and then in order to look only the valid pixels and mask the other one. So I will do it really quickly. For example, I will take these 3 values, we suppress them, and we can just set the other value as black. And yeah. We're going to do that for the other one. So in black, we have every pixel corresponding to vegetated and water area that has been transparent, so we can see the background with the true color image. But every clouds have been masked here. But you can see some artifacts as well. I will just let still do it again. Up. We can see some artifacts here. So we can discuss. Do you see that as well? In your opinion, why is there some so 7 corresponds to the cirrus and clouds detection? In your opinion, what is the cause of this? Why do SCL detect something like that?
I mean that the green on top of the detection of the cirrus clouds, there's also false detection of the cirrus clouds. And you're asking what?
What could be
what is detecting?
Yeah, exactly.
Detected, sorry. So do you have an idea on what is detected with the cirrus cloud in the light green, so class 7? No idea.
When you see this part in green, they are all located. It's not cloud cover, actually. You can see that it's located in a particular area.
It's only coastal?
But it's not shadow as well. But you can see this green area here. It's, as you can see, it's near, it's water. Rex give us, I think, a clue here. It's area between water and land, as we have some probably some indicator that as there is a lot of water here and also some close by land, it can trigger probably the classification algorithm to detect is that thin cirrus. So just to say that we need to be careful using this kind of data, this kind of data as mask, because everything is not perfect. But at least, as you can see, for the other type of shadow and clouds, so I will remove the 7 because we see there is no cirrus as well. For this kind of clouds, there is quite a good detection. And in pink, there is a cloud shadow. So it's quite important to yeah, it's quite interesting to use it. And we will use it later in order to remove clouds from time series. Okay, so we just look at the first part, which consists on the SCL and true color. But now we can dig a little bit into indices. But first, I will ask you: does everyone loaded SCL and could only visualize the clouds using the method I just showed you before? There is 8 answers are at all good.
We need to go to 10 before moving.
Yeah.
Come on, yes.
About 10.
But if you have if you need some more explanation, just don't hesitate also to say no.
So okay, we will now go into the indices part. So we just did the first 2 parts of the exercise, but as you can see here, we have the description of all Sentinel-2 bands and some indices. So what I propose to do is we're going to do together the NDWI. So it's this formula that I will copy paste into the chat for mine, and also I will copy paste. I can do something more clever actually. Up, we are going to. So in the chat you have an image with the current slide in order to use it as our reminder. And so we will use the spectral bands in order to create the NDW index. So I will just put this on the side. So NDWI, it's green minus near infrared over green plus near infrared. So indices are quite interesting because they can allow to remove some artifacts, and they are very often used in for a particular topic. For example, NDWI is used very often in flood detection or for water detection. Basically, it's an index based on some bands to detect the water. So the idea is to load first the band that we need. So NDWI, it's green, so it's band 3, and near infrared, which is band 8A. So we'll stay in the 20-meter resolution folder. because it is much more quicker this way than using the 10-meter resolution. And for the exercise, it won't impact much. So I will remove this. So we have the near infrared band here, and so you can see that the vegetation has more higher value because there is more reflection in the infrared domain for the forest and trees. Whereas in green, it's very dark because everything is absorbed by the vegetation. So we'll use this to do our index. So we'll use the raster calculator, which is located in raster on top of the software, and click on raster calculator. And so it will be band 3 and band 8. So we'll place the brackets because we have red, so band 3 minus band 8. And it's the same thing, so band 3, the green, plus band 8. So we cannot let the expression invade, but we cannot export a link. It's normal because we don't have chosen to create an output layer. So I'm not in the right folder. Sorry about that. So we're going back into the training. Okay. The WI. Okay. And then we can, once we have our output layer file path indicated, and we have the right expression, you can do OK, and then it will calculate the band ratio. So depending on the complexity of the equation, it will spend it can spend more time doing the calculation. So we'll wait a little bit. So it's a first example here, but in the land cover services, these three are used into the chain, these three indices, plus only the spectral band as well, the pure spectral band. So we can do it in combination for a classification purpose. So yeah, it takes just a little bit. So everyone has started the expression, the raster calculation.
Carla, can you maybe send another poll? Just if Etienne needs to re-explain some of in this calculation, if it's okay. You have some questions, Etienne.
So there is two questions. When do we use QGIS over Google Earth Engine? Actually, I don't choose QGIS over Google Earth Engine. But do you mean, Rex, can you be a little bit more precise? Because for me, you cannot use QGIS. Maybe there is a module to link Google Earth Engine with QGIS, but I am actually, I don't use it this way. So maybe there is a possibility.
The question for me. Sorry, I think Etienne. What I understand is you confirm, Rex. Is it when do you use QGIS instead of Google Earth Engine? And when do you choose to use one of the other? Would it be the question? Or Rex, you can also open your mic if you want
yes.
to.
Okay. When do we use it? Okay. So actually, QGIS here we use it on the single images, but Google Earth Engine is much more interesting when you want to do a calculation, because there is free resources. From what I understand, what a lot of people do for the calculation on a big data set, which use a lot of data. And so I would say that for us, it's just for one image here. But if you want to do a batch calculator, so cloud services such as CreoDias could be used as well. I know there is a OpenEO possibility, which is a big platform that brings different services such as Google Earth Image, Google Earth Engine, and other such as CreoDias as well, cloud services. So that's the main difference. So there is two questions about the output layer. So for me, when I create the output layer, it's the name of the file and that you use and that you look at when you create your index. So for me, I created so I click on this and I created the NDWI file. So if you want to create this,
so you just create the name that you.
Okay, you just create the name and of the file you want to create, and then you do the calculation. Need support in finding the right bands. Okay, I will show you again. So I wrote the output layer here, and then for the calculator, it's quite simple. We have as we put in the chat, we have two spectral bands that we use in this expression. So it's green corresponds to the band 3 for Sentinel-2. So you click on this and it will appear in the expression below. And for the band for the near infrared band, it's band 8, and then you click again, it will appear below. So you just need to add the sign corresponding to the equation. So red minus near infrared over red plus near infrared. And then as everything appears here, you just finish the equation and click on OK. And then it will save the results in the file we just enter it. So you obtain this. You should obtain this. So this is the NDWY, so the normalized difference water index that shows with high values correspond and values above 0 correspond to water areas, and below 0 corresponds to land areas. So we can click on this, or do a right click and properties, and we can do a little change in the symbology. And for example, we can use this color band and can be a little bit more interesting. So we can just set also the limits of the color band in order to change the visualization. For example, if we want to have a clear distinction, we can do just a smaller range, so between minus 0.25 to 0.25. And yes. Does everyone succeed to obtain the NDWI? We have an instant poll coming in.
Do you have any more questions on this section about calculating the index?
I'm sorry, I just have a cooking emergency. I will call you just in 1 minute. I'm sorry, I'm coming back.
And it gives us some time to answer the poll. So if is everything okay so far, you can answer with the yes tick, or if you need some explanation again, the cross. We have to reach 10 answers to have Etienne back. So I see there's a cross. Do you want to ask your question in the chat? What we've been doing now is manipulating the Sentinel data. So Etienne went through the, in each of the file that was already prepared in the folder. You see that each Sentinel-2 tile file or folder contains a series of bands. So it contains all the bands of the different wavelengths. What we call the band 1, 2, 3, 4 to 8. So first we manipulated the bands to see what they contain. So some of them are related to top of the atmosphere correction. We manipulated the different classes of this band layer to see the clouds appearing, or to prepare some cloud mask. And then finally, we combining different bands, we were allowed to calculate an index. So for the exercise, it was the NDWI, so the normalized difference water index. And you can also do the different you can also try to play with the different indices. So I can see there's some question. The link for the 5. Okay. Carla, do you have it, or I can find it?
Already sent. Yep.
So we have some interesting results. So now with this particular index, you can really, so as Etienne mentioned, so this is a different water index. So we really focus on the different values that will highlight the areas where there is a lot of water, or areas where there is no water. So you can see that here, all this northern Bay of Manila, with the more watery area, while the vegetation is in red with no water. And we have 10 people answered. Not really, but we can still continue.
Sorry about the disturbance. Thank you, Marion. So
Okay,
I think we did manage to have the index. So we won't do the 3 indices that has been proposed in the slide, but rather we continue to look at the Sentinel-1 dataset. The Sentinel-1 dataset is shared the same way as the Sentinel-2 data, meaning it's based on the MGRS military grid reference system. So everything is cut on the same way, but Sentinel-2. So it's really nice to have the same cover for both sensors. And so the Sentinel-1 sensor is performed to add different, it can be used within different modes. And the one we use for land application, it's the interferometric wide swath mode, which has a resolution of 5 meters within range and 20 meters in the azimuth, meaning that along track of the sensors, it's 5 meter resolution, but across track, it's 20 meter. But for simplification, everything is degraded to 20 meter resolution in order to have square pixels and not rectangle pixels. And we have HH and VV polarization, HH and HV polarization in the end. So Sentinel-1 is interesting because we can have some data below cloud cover. And the data I will show you here is everything is located. So we come back in the ArcObserver EO folder. The EO folder image. Everything is in Sentinel-1. So you have here 2 images. The name corresponds to the mode, so IWI, and M01 corresponds to the month of the year. Here is for January 2023. The thing to know, the image we use here came from the Copernicus data space, and it corresponds to a mosaic of aggregated data for the month of January. It's better for several things. First, we have a lot of pre-processing in radar data, so it allows us to avoid this step because it needs high EV computing in order to do the pre-processing. Plus, having monthly aggregated data sets, it's really interesting because it gives us less noisy data sets. And then you have the name, so 51 PTS of the tile. So we click on it, and we have VH and VV. VH that corresponds to the polarization VH, meaning that the sensor will send the vertical signal and receive horizontal polarized signal, whereas in VV it will be vertical send and vertical receive. So we will load the VV and the VH. So as you can see, we don't have, it seems very black. And it is due for a reason. It's because we don't have the right symbology in order to represent the data. And as everything is expressed in linear scale, we'll have really a few values on top with very high values, and then that causes this kind of symbology in QGIS. So what I'm proposing is to change the symbology for both. So to switch from your scale from 0, so you're going into symbology, you let in single band gray, to 0 to 1, and then you apply. And then for VH, as we have less signal coming from the horizontal polarization, there is few signal between the cities, but we can see that, for example, there is every built-up areas are very nicely visible here, and we can do the same thing for VV. And so you can see here for the vertical received, there is more, as it's a vertical send, there is a lot more signal coming in this way. We can see that so built-up areas, as I said, are really visible instead of land areas. So the thing is, this representation is quite interesting when you look at urban areas, but to look to other kinds of land cover types, we can use over-representation, and we'll use the raster calculator to create a decibel, to convert to decibel values this raster. So we will use the raster calculator with this expression. So use the VV band, and we need to apply this expression, 10 by logarithm of VV. So I will let you maybe 1 minute try to do this using the raster calculator that we used just before for the NDWI. You can use this for the VV, for the transformation to decibel. So I will give you 1 minute to do that, then we'll do it together using the raster calculator. does that mean the cat is value, the 4 value is the outlier motor of the tile is in the range of 0 to 1? Yes, exactly. Exactly. There is some, in radar, we have some very high reflective targets. You can see boats, for example, which are really, really visible. In particular, in individual image, here we have an aggregation of several images, so it's less visible. But we can see some very high reflective areas such as antennas, something like that, which can be troublesome. Okay, so we will with Vivi start the transformation to decibel. So it's 10 by log of Vivi. And for this time, I will create an on-the-fly raster, meaning that it will write it on the temporary storage, and then will be destroyed at the end of the session. And then do the calculation. So you see, it's quite different. As Rex mentioned, so there are some outliers, and you can see here an example of a very high reflective target because we have a nice cross here. But in decibel values, we can see a little bit differently the areas. Some area for grassland, for example, are a little bit visible, more visible. If we can just look at this, for example. Yeah. We have some grassland here, which are a little bit visible with the decibel visualization. So yeah, it's quite interesting to change it. And we can compare that the distribution is completely different by looking at the histograms. So yeah, please feel free to share your results and show us your maps that you produce. Thank you. And so you're going to properties and then in histogram, and then you can compute an histogram. And as you can see, there are some, here we can see a double mode of histogram values with a first peak around -20, which is actually the water areas where there are negative decibel values. So it's mainly water areas around here. And this is land areas around -7 decibel. And when you compare it to the VV histogram here, we can see that it's quite different. Sorry. So we have the 0 here, and then we see that all values are ranged between 0 and 0.4, and then very few values when we have a higher scattering value. So when you are faced to classification task using Sentinel radar data, it's more interesting to use this decibel range than use it in regular values. Okay, so from what I see, we are quite advanced on the indices creation and about with Sentinel-2 and with Sentinel-1. Do you have any additional questions? Something you want to share maybe? And if not, we're going to pass to the next part. But first, let's wait from your part if you have some question. Okay. I would like to ask what most white streaks are around the mountain to the northwest of the map. Northwest. You're talking here. North streaks.
White streaks.
In the. Can we set it min-max automatically around -2 sigma plus 2 sigma? Okay, there. First, the question. Oh yeah, these. So it's one of the effect of radar actually. So the white streaks here is because that's an artifact of radar. When there are some slopes, there are a more important reflection of the signal coming from when the slopes are face the sensor. So meaning that on the slopes you can have some, so there is some correction in order to remove that, but it's not always possible to remove everything, in particular in very important slopes. So I know here we are in a crater, so it can create this kind of artifacts, which are quite important in VV, but not in VH, from what I remember correctly. No, so yeah, no, there is no data here. And second here, I mean, it's automatically removed. There is no data here. It's not white, but you see some artifacts staying there and there. But the white part here, it's because it's no data. The thing we can to show you what's no data, you just select the band, use the little information identify feature here, and then click on the part you are interested in. And it's white because there is no data, because it's wrong data value actually, and it's automatically masked in the process. But it can appear white because it's very important slope, so it can have very high reflective values, which don't reflect the state of the land cover below. It's mainly the terrain that does this kind of artifacts. We can set the min-max automatically, or yes, we can do that. We can totally do that. If we go to symbology, you can go to min-max value setting, and you can do it by around min minus plus or minus standard deviation, for example, or using over settings here. You can use the min-max, the cumulative clone count. Yes, so we can do that. And when you have 2 standard deviation or something like that. You're welcome. Additional question? Okay, so maybe we'll go on the next part. So for the next part, we will talk about reference dataset for training. Why are we talking about that? It's because we need an accurate set of reference data because it's really important to have it to produce accurate land cover map. If we don't have really good reference data representing the right classes, it could be troublesome for the machine learning algorithm. So here I will present some tips, and then we will manipulate some data in order to have a good to show you what is a good reference data. Reference data set. So we have different way of creating this kind of data sets, different sources. We can use it from in situ measurement, from fieldwork. I know that in Amria, a lot of people are doing this fieldwork. There is also the possibility to doing it using VHR images with technicians and photo interpreters looking at images and identify each classes corresponding to the land cover class, for example. And there is also the possibility to use external data set and in order to add some more info. For example, here we have the French land parcel identification system, where the equivalent of the IRS retrieve the information from each farmer in order to know what they are growing. So here is an example in Brittany. So the idea is using these data sources to create a shapefile. And to create the shapefile, it must contain several fields. A code field which corresponds to the class label. So, for example, for Namria, the class label is closed forest and the code field is 1, and open forest 4, it's 4, and so on. Another field that is interesting, it's a surface field, which is calculated at the end of production, and it allows us to know the surface and the area of each polygon. And in option, you can add a depth field, which is interesting if if you need to know if you trust your data, and especially for some polygons, if you have some doubts, it's interesting. And use a projection system. Here is an example we use for the land cover service. Is the ground truth manually and annotated in the VHR image? It's more about using the VHR image to create manually ground truth, if I may change the sense of the sentence. Meaning that, yeah, for machine learning, it needs some ground truth data, so reference data, which is for the time being manually obtained for the most part. So some other indicator, some other suggestions in order to create this reference data set, and in particular for the polygon drawing. In order to have some enough pixel for in each polygon and to avoid mixing with the border and other classes, we need to have at least 1,000 square meters minimum for each polygon. So for us, it's 10 Sentinel-2 pixels. But depending on the classification task and the data you have in input, you can adapt this. For us, we set it to 10 Sentinel-2 pixels. But if you use over data, you can have an area quite less. If you have more high resolution data, for example, if you use Pleiades images, it's a sensor with resolution of 50 centimeter. You can use at least 10 times this surface because it's much more precise. But for Sentinel-2, at least to have polygons of 10 pixel size, so 1,000 square meter. Also, you need to have homogeneous areas in order to avoid border effects. In this example on the right, you see that the polygon are both. Here you have some forest and some crop here mixed in the same polygon, so it needs to be avoided. Also, the filiform shapes needs to be avoided because in this particular case, you have some over classes that are mixed inside the polygons, and as the filiform shape, as the shape is filiform, there is some mandatory mixes with the neighboring pixels, so it has to be avoided. And same as the minimum surface area, but you need at least 20 samples per class and per Sentinel-2 tile. If you want to do it on several tiles, you need a lot of data. Of course, you need to adapt this depending on the presence of classes. For example, if you are in the mountainous area in the middle of Luzon and in the tile there is no mangrove, for example. Of course, you won't take any mangrove, but it's best to have it. And the question that I saw, it's to have 20 samples per class. It allows us to have a more quite an homogeneous presence of the samples over the tile, over the image, in order to have quite the spectral variation and spatial variation for the same class. So the idea is to have something quite homogeneously reported on the map. In order to have something, we have the spectral and spatial variation for each class. For example, if you have some differences in forest in the same on a big area, we can show it and add it inside the reference dataset. And last set of suggestions is to carry out a topological check to ensure that there are no more overlapping geometries or invalid geometries, such as this one where there is self-crossing, no duplicated modes, no overlapping like this, and no filiform shapes. And last but not least, to document the data source used. For example, if it came from images or for exogenous data and so on. So now we have all these ideas in mind. We can try to do a little bit of work and try to exercise ourselves into check the reference dataset. So we'll open QGIS again, and then there is two things we need to install. First, it's a quick map services module, which allows us, as we don't have the HR image for this for this task, we will use some background images from Bing services or for Google Map as our reference data in order to check our reference data set. But it's not recommended because you won't necessarily have the rights, and of course you not necessarily know the date of the date of acquisition of these images. And then there is another tools you need to install. It's Geometry Checker. So I will just show you how to install it. We will go to plugins on top of the software, manage and install plugins. And in all, you're going to type geometry checker, and you click on this for geometry checker. And same thing for quick map services, and you install it. Once you install quick map services, you should have web quick map services appears. When you have a geometry checker installed, you have check geometries in vector. So if you have vector check geometries, means that everything is installed, and web quick map services as well. Okay. We have 9 responses in the poll. Those the other attendants. Okay, I see that other people loaded the reference data. That's great. Okay, we are at 10 responses. Okay. Then perfect. So I see that we can add as well the reference data inside the QGIS project. We can also add using web quick map services and, for example, Bing and Bing satellite, but you can use another provider as well. And we can have a nice overlay under of reference datasets. And especially it's interesting in order to see the accuracy of the reference data and see which classes are below the polygons. We can also load some style that has been created previously. So you're going to symbology, and on the bottom there is a style button. You click on it, a load style from file, and you choose the file which is located in reference data and style samples and load style. And you have this. Okay, so one of the first thing we're going to do is calculate the area field in order to see which are the size of the current polygons which exist on this data set. So what you're going to do is to open the attribute tables. So right click on reference data, open attribute table. And then you access the reference data. With the little pen on the left, you click and you are able to modify the shapefile. And then using the little hibiscus here, which is a field calculator, we can create a new field. So a new field is a new column in this data set. So we know that it's a decimal number. We want a decimal number field. It's an area field. You just need to integrate the name. And then in here, you can see there is a geometry possibility. And in geometry, there is area. You click on area. And then you just need to have OK. And you have all the area calculated, the surfaces calculated for each polygons. So does everyone still following? So yeah, once every surfaces has been calculated, you need to sort everything just by clicking on top of the column. And you see that there are some elements that have an area under 1,000 square meters. For example, this one has no area at all. And so we can just look at it, for example, using the zoom map, which is the little loop here. And so you can zoom on the area and you see that it's a weird polygon which doesn't have any surface. There is other places with other polygons very weird. For example, this one is really small, and it's not a problem in itself because it's in the middle of the quite homogeneous land cover type. But it's best to have at least to contain at least 2 or 3 Sentinel-2 pixels. So it's not recommended to keep it. For built up, it's also, I think, a good it's well classified. But the thing is, as it's under the house is under at this the requirements of the minimum mapping unit, you have some problems. You will have some problem of mixing with the neighboring Sentinel-2 pixels. So that's why we prefer to have like clusters of houses to be used in the classification in the reference dataset. I hope I'm clear enough. We have another part here, which is also have a weird shape. So same, we need to remove it. We have this one, which also has a really weird shape. And this one, which is built up, but really close to the really size really small for us. So there is 2 different things. You can select all of this and then suppress it using dated selected features. But we will use another tool which allows us to see also some incorrect geometries. And this is the geometry checker. So solution number 2 is to use the check geometries tools. So does everyone has this tool installed? Is this okay? So this tool is quite interesting because it allows us to do as well as a topological check to see if there is some invalid geometries, but also to detect some minimum areas that we need to remove. We can remove the filiform shape, so the slivers polygon, and you can change the finesse also of the polygons, the minimum finesse, the maximum finesse, so the minimum thickness of the polygons. So we choose to only detect self-intersections and polygons with less than 3 nodes. And we can also add self-contacts and duplicate nodes because it's also in the invalid geometry as well. And then we can see that everything else is okay. We can modify an input layer or create a new layer. So if you create a new layer, you can browse, and you can create. So you can choose the folder where you will save the dataset once everything is corrected. So for example, I will create an output folder. Yes, and select this folder. Okay. And then we can run everything. So the first step, it will detect every problem in the polygons that we decided to look at here in the setup part. So every parameters here, it will detect the issues. And then we will fix the error, whether one by one or all together. So we can see that we have several errors, and we can click on the data to detect which one is it. So for sliver polygon, we have this, and this. So it's the polygons that are too thin. We have self-intersections that have been detected. We have this one. So we have also this one. And these two, so we have at least 3 objects that has been detected with incorrect shape. And we have also some with the minimal area. So these are the one we look at it earlier. So it's an interesting tool because it allows us to do everything at once. So to solve everything, there is some set of rules. So you're going to the error resolution settings here, and you click on this. And there are different types of resolution depending on the type of error. So I hope that everyone can see it because it's a little bit small, but for minimal area, we choose to delete the features, but you can do other things. For example, to merge with neighboring polygons if there are some, but it's not the case here. For polygons which has only 2 nodes or 0 nodes, we delete the feature as well, the sample. The same for duplicate node. And for self-interactions, it will split features into multiple single object features. I will just change that. For sliver polygons, so thinner polygons, we just delete the feature as well. And geometry type, so it's a problem of format here, so we won't change anything in the geometry type because it's just a question of format, so it doesn't have a real impact on what we want to check. So once you correctly set these settings, you can fix the error. So you can select everything with a Control A, and then fix selected errors using default resolution, and then you click on this. So we have 113 errors, and you click yes. So it will do the correction one by one, and apply the resolution that we decided just before. We have a little time. Does everyone still following at this stage? Once we wait for the results.
Any question on the check geometries tool? Carla, maybe can you ask if Etienne needs to re-explain, or if it's okay? Or you can also just type your question in the chat if you want to Etienne to re-explain some of the particular section. So while it's calculating, so Etienne, all this data preparation that you are showing, so this is an essential pre-processing of the reference data that we need to do before doing the classification. So if you can confirm that, and also, do you use is QGIS really like the necessary tool? Or I mean, you will do the when you do the classification, do you have to go through this process of cleaning the data in QGIS, and then is QGIS a good tool to do this data preparation with the tool you are showing?
I think I will answer you by saying yes, it's a good tool to prepare the reference data set. But I mean, we are looking at the way as just to check the data set. I mean, we can prepare it on the other way, for example, with a field campaign, or with people on ground doing some GPS acquisitions, for example, or but for photo interpretation, and I think QGIS is quite a good tool. But you need to have some VHR image with the date, the most closest date necessary in order to have the most accurate reference data set. That's the only problem I see it. But yeah. Because the format you create, for example, with Google Earth Pro or tools like that are not in a good format, or not KML, for example, are not really easy to use. So I will engage more. I will more into the favor in favor of this kind of tool like QGIS.
So this pre-processing.
There is some GIS software that exists, like ArcGIS, which is really nice as well. Here, QGIS is really easily accessible. That's why we're doing the course on it, of course. But we can do the same thing with ArcGIS. Yeah.
And so this pre-processing of the reference data, this is a task that we need to conduct before running the classification. And when we'll be running the CopPhil service will be the next step. So all the preparation of the reference data will have to be done prior to running the service.
Yeah, exactly. I mean, for the data preparation, such as NDVI correction, for Earth observation, everything is run inside the land cover service, as well for the classification. But the only part that the user needs in order to run the chain, it's the reference dataset. So yeah, it's quite important to have a good dataset, because also it's one of the part that the user brings, and that will impact really importantly the result of the classification. But would it be all right to review the setup for check geometry one more time? Of course not. We can do that. So just we have some results here, but we will show it again. So for the check geometry, when you click on the tool,
you have to open. Sorry, just the previous step. So it's under vector.
Yeah.
And then you open
check geometry, which is just here. So you open it, and you will have this window to appear. When you have this, you click on the data you want to check. So here it's reference data, and you select the kind of check you want to do. So we want to check the validity of the geometry. So if there are these 4 parameters to check, and also the geometric condition, in particular the size of the minimum size of a polygon. Here it's 1,000 square meter. and also the maximum thickness of the polygons. So in avoid to have to the minimum thickness of the polygon. So here we set it to 20 meters. So once everything is set, on the bottom you have the output directory that you need to choose, and then it will add a checked prefix to the resulting shapefile that will be created. There was one question that popped up. No,
it was me, but okay. Well, I'll just ask while you are setting these values about the minimum polygon area and the maximum thickness or thinness. Are they recommended value, or this is something that what would be the how would you define the minimum polygon area?
So it's something where I will just talk just earlier. The minimum area will depend on the sensor actually. For Sentinel-2, as we want to have at least, we will have a 10-meter resolution. We want to have at least 10 pixels falling inside the polygons in order to have quite a good variation of the spectral variation of the object and to minimize the borders effect. And also the same thing for the minimum thickness. It's 20 meters because we want to have at least one entire pixel inside the polygon. So once we set the output, we need just to run everything. For our side, it's okay. And so you should detect a lot of error. So we can look at the error by clicking on the so mine are soft, but you can see that it can automatically zoom on the samples that have problems. And then to once everything error are detected, you just need to change the resolution settings. So how you will manage the correction for each type of problem. And so we chose this. So actually we kind of delete the features for all problem, except for geometry type, because it's just a format error in our case. So we don't want to delete the features. Or you can, and for self-intersection, but it's because we have no choice than to cut in the polygons in several polygons. So once you have the error resolution set, you can just select all the error by Control A, and then fix the selected errors using default resolution. So this line, the first check in green, and then it will solve the issue, and then we will look at it together. So it's a question from Carla. So if we want to use our own reference dataset, the same parameters using geometry would apply. What would be the factors to consider or to check? Yes, the idea is to create. I mean, I'm not sure to understand the question, but from what I'm understanding, it's if we want to create over reference dataset without using check geometry, because check geometry is like okay, yeah, we use check geometry in order to verify a dataset. But if you created your dataset from scratch and you use the parameters I showed you before, meaning the minimal area and avoid the topological problem, theoretically it should be fine. But as error is human and operators are human for the time being, it's good to always check at the end of your work. Especially here, it can take 5 minutes with this tool in order to check if there are some problems anyway. It could have some problems, or if everything is all right. So we have everything solved, it should be. And so when we look at the attribute table, and we see that the minimal area here, it's 1,900 square meters. So apparently seems to be okay, and everything seems to be corrected. Do you have any more questions? Okay, I think it's okay. So maybe before we go on the next part, we can do a little break. So for the next part, it will last around 1 hour. So probably we can take 10-minute break if everyone's okay.
Hello, everyone. So welcome back, and hope you had a good short break and were able to stretch a little bit. So 10 minutes has passed. So let's check for Marion and Etienne. Here, perfect.
Hello, everyone. Welcome back. So now that we just saw the inputs of the chain, so namely the Earth observation datasets that have been used and the reference dataset as well. Now we'll talk a little bit about the CopPhil Land cover chain. So the service is based on IOTA2. IOTA2, which is a toolbox created by CESBio, which is a laboratory in France. And it is designed to use time series in order to create land cover maps. So it uses random forest classification, machine learning tools to create land cover maps. So it can use both Sentinel-2 and Sentinel-1 image, for example. And it's a pixel-wise approach. It uses time series to fill the gaps. Yeah. So the idea here, so the classifier, the machine learning consists in random forests, which is an ensemble of classifier with several decision trees. And each decision trees allows to select samples and to delimit some classes the most decision tree, so the most tree you have, the most precise will be the classification, but the most heavy it will be to make it run. So it's one of the most important hyperparameter. Also with the number of variables used to split the decision tree nodes. So here's a little example of the random forest. So it is used because it's an algorithm which is quite robust to overfitting, and so that can use a large amount of data quite easily as well. So we dig into these two parts, so the time series and the random forests classifier with Google Colab. So it's a Jupyter notebook which is hosted on Google Colab. So what we will do is first add the CopPhil training practical folder in your drive. So I share the link in the chat right below. So it's in two steps. First, you need to, once you open this link, you click on the name of the folder, and then you click to add shortcut. And then you select My Drive. So CopPhil Training Practical, Add Shortcut, and My Drive. We have, yes, the CopPhil Training Practical. You're right. It's the one you need to add. It should appear in your drive like this. In My Drive, you should have something like that. Sorry, you should have something like that. And you need also to get to import the Google Colab notebook. So I will share again in the chat the link. And then first you open it and then you copy to drive. There will be a copy that will open in a new window. And in the same time, it will appear in your drive as well as a copy of CopPhil Land Cover training course. So I will do that as well. So I don't, I'm in French, so copy to drive or import to drive is the same. So you click on this. It will open a new collab that will appear now in your drive. In your drive, you will have collab notebook and copy of land cover training course. Can we do a little poll to see if everyone is okay at this stage and just yes or no? Are you? Yes, thank you, Carl. Yeah, seems that at least 8%, 9%, and then we can start the session. Okay, so maybe we will continue. We will just look at we will look at time series and so on. So we will together trigger the cells for each in this Jupyter notebook. So everything is written in Python 3, and all libraries exist are open libraries. So we will this first part is to install the libraries and import them into the environment of the execution. So there are 4 types of libraries. First corresponds to geodata management. So basically, it's everything that's needed to handle geographic and a geographic data set or remote sensing images in this case. So we have radio X-array, which is been used to open image, for example. X-array, it's a library that allows sorry, things triggering that. X-array is a library that is really used in order to open netcdf format files. There are some libraries to use to open vector files such as Shapely and GeoPanda. There are also a set of machine learning libraries that are used for the random forests. Some libraries to plot the data. And then in the end, there is some data management library and other libraries such as NumPy, which is a very common library in numerical processes. Final part is to mount the Google Drive. So the Google Drive, we now have access to the dataset that we will be using inside the drive, but now we need to link the collab to the drive. So we trigger this cell and it asks to connect to Google Drive. So yes, you say you want to connect. You will use your account. And then you say okay about the condition of the terms of service, and you continue. So there are, if you didn't use Collab before, there are 9 little button to check here and to accept, because otherwise, if you don't accept everything, it cannot run correctly. So I engage you to check everything and then continue. And then it should. Okay, and now mounted should appear. So let's look at time series. In order to avoid AV process such as stacking all bound together and creating index on the spot, I took the liberty to already do that and store everything into an etcdf file, which is called Sentinel-2 mouse indexes. So we'll open these data sets. And you'll see that there are 3 variables which correspond each to 1 index. So the NDVI, the normalized difference vegetation index, the water index, the normalized difference water index, and the burnt soil index, the bare soil index. BSI. You can see that the dimension of the dataset, so there are spatial dimension, X and Y, and the time dimension, which corresponds to the number of images that has been used. So which image do we have? So we have, actually, it's not only one image, but it's aggregated images, monthly aggregated images for each month. So we have 8 months of data between January and May, and then between October to December, in order to avoid the high cloudy period in the highly cloudy period in July to September, June to September. So if we just select one time period, we can plot really easily the index. So it's the same as we did earlier, but everything in Python code. So here you can see in NDVI really high values for the forests around the mountains, and low values for the sea and for the built-up areas. So you can play a little bit with this. You can try different dates. For example, how everything looks in October after the rain season. So you can see that, for example, there are much more higher NDVI on the ensemble of the image. Probably the wet season, because the wet season has passed, and that the grassland are dry anymore. So there are some changes in time in NDVI. We can do the same thing about Sentinel-1 time series. So we can load it as well. So you see that this time there are 12 images, because one per month, because as we use Sentinel-1 data, we don't have the problem with cloud cover, as we can retrieve data under cloud. And the variables VH, VV, as you saw earlier, and then a ratio between VH and VV. So same thing, we can plot just one image to see how it looks like. So for VV, same as you did with QGIS earlier, but we can also do a check with a more elaborated plot with 3 colors corresponding to VH and VV, and so we can see a nice variation depending on the area. Yeah. So once everything is loaded, now we will use the reference data that has been already sorted, but with the step we did just before. So we load everything. And we can sort everything, for example, by size, and see the different polygons here. So we use GeoPanda, which is a really interesting module in order to manage vector data in Python. So, and then once every polygons are loaded, we decided to pick 100 pixels in each class. So we will randomly select, generate these 100 points. And so we'll have for each class 100 points. So you can, that you can see here. So this step is to the idea is to have these points in order just to retrieve the pixel values under these points instead of to have a set of points. So now we can go a little bit further and look at the time series. So first we check we load we try to retrieve the data, the Sentinel-2 values beneath the point we just created. And now it should appear in the geodata frame. So we'll have for each point and a series of time value for each time a value of NDVI, NDWI, and BSI. So for each point. And then we can look at the results quite easily and see the differences. So it takes a little bit of time to plot, but everything should appear. So we have only 10 classes on the area. So we have 10 classes here. And we can also see some differences. For you, which classes show the less variation and from all these classes through time? Yeah. Or just to tell you that between May and September there is no data. So this part actually there are lines, but they don't correspond to actual data. For example, for built-up. For the variation through times, it's true that mangrove forest has really few variation, but whereas, for example, grassland has big changes in time because it dries and then after, as we saw a little bit about the two NDVI images before, there are a bit more of vigor after the wet season. But and also the forest has only really few variation. I suspect there are some outliers here, but we need maybe to dig a little bit more in the dataset to see where it comes from. We can see also a nice temporal variation, but very mixed for the annual crops because we have different crops in this. So with different phenology. So, for example, if this one is I don't know, yam, for example, and this one could be rice. So it really depends on the seasonality of the crops. So that's why there is a high temporal variability here. For brush shrubs, we see that there are not a big temporal variation, but there is a big NDVI differences and it seems to have two populations of brush shrubs, so something to be investigated as well. And we have other classes built up, for example, where there is a large variation of NDVI, probably depending on the quantity of vegetation between the houses and the blocks. We see some variation in inland water, but could be due to discharge, like sediment discharge or things like that, which change the color of the water. Whereas fish pond, there are less variation; it's more stable. And for perennial crops, there are less temporal variation as well. So yeah, it allows us to understand how everything changes depending on the class. We can do the same exercise for the backscattering coefficient, so meaning with Sentinel-1, but maybe we will pass because it's not that interesting, and then we need to look at after the result of the service. But for now, we will go into the machine learning part, where we need to merge both Sentinel-1 and Sentinel-2 datasets. So we'll have the final datasets here, and how it works. So we have a bunch of functions here, which basically are divided in 4 steps. First, it's we select the feature used for the training the random forest. It's kind of the same work as we did earlier, meaning that we just pick the values and arrange it in certain ways in order to feed the random forest. Then we have another function to train the random forest algorithm, and it's where you can change the parameter. So the estimator are the number of decision tree, for example. And then last part, it's to predict using the model we trained just before. And then we plot everything using X-array. But this part is optional in this particular case. So let's do it. So we have the function before, and now we have the command line. So we launch everything. It will take a little bit of time, and then we will plot the results here. Do you have some question when we wait for the results to come? Does everyone run the collab smoothly?
Do you have any questions about the time series that we've seen before? Is it clear for you what was this time series allows to analyze?
So we have a question in the chat. Yes, in the ideal world, you need to separate the data to train, validation, and test. That's exactly right. But for the time being, as we don't have a lot of training data on the data set, we use everything to train the model in this demonstration. But you're right. In order to predict the accuracy of the model, we will need to separate between train and test. Not necessarily in VAL, but because VAL is for much more deep learning algorithm, if I'm not wrong. But yeah. Need support on some cells. Is there a problem of running it from the people who need support of some cells, or some additional explanation?
You maybe mentioned the cell that poses problem, or is it some errors that you get in the running?
Okay. Sorry, one of the cells just took a white one, but now it's okay. Okay, no problem. We are here for that. So that's one classification we just made. So you see that there is really few land closed forests in this part. And when you look at, and I will just spoil you a little bit. When you look at the NAMRIA reference land cover map, we see that there are a lot of closed forests around this area, whereas here it's kind of small patches. Also, there are really large grasslands. So I'm not sure it's the case. Yeah, no, the grasslands are quite okay. So probably the results are not optimal. And as one of the participants said, there are we need to do some accuracy testing with more data sets. Yeah, we don't have a lot of data to train, so we don't do that. But we should have. But in your opinion, what should have? What are the main key to improve the model, in your opinion? What should be what it should be, in your opinion? I see two main keys where you can improve the model, but can you find it as well? Do you have an idea?
Any suggestion on how to improve this first classification? Maybe we can keep the question for later after the
yeah, maybe
explanation on the confusion matrix.
Yeah, but what we can, yeah, probably. Yeah, cross-validation, you're right. But what I wanted to say is it's that to improve the results here, we can use both change the hyperparameters of the algorithm, or increase or change the training data sets that are used, yeah, and more features. So that are the two main things that you can do to improve this kind of results. Okay, that's it for the Google Colab part. Now we will come back to the results of the chain. Of first, how it's launched. So it's a free. Actually, there is three tools that are used to launch the tool. First, it's S3 bucket, where the user prepares the configuration files. For example, the AOI that has been used in order to select the area of classification and where to export the results. The second part corresponds to the launch of the chain with this API. And the final part is to track the error using the Nomad API. So I will just present you how to launch the chain using the API. So there is when you access the API, you see this page where you need to connect, and there is a simple command that you need to do. It's just to change the request body that is here, which correspond to different parameters. Basically, you need only 4 parameters. This one is not. Sorry about this one. You need to really change 4 parameters. First one is the year of processing. Then, for example, you need a land cover map for 2023. So you enter this parameter. Then you indicate where you want to send the notifications. The ROI, so the shapefile defining the region of interest where you want. The last part, which is clean directory. If you're the process is quite easy because there is a lot of pre-processing and the processing is uses quite a lot of resources. The clean directory allows you to remove and to clean the directory where there are temporary files stored. But if you want to do several runs on the same place, you keep this at yours, and then it allows you to speed up a little bit the process. And then there are the S3 credentials in order to connect to the S3 bucket where you will retrieve your data set. So once everything is launched, you should have a responsibility as 200 and that everything is successfully triggered. So now, after everything is launched, it takes several hours, but in the end, you'll have your land cover map, and it's divided in three data that I will show you just now. 3 results, 3 products. So, so you have everything in IOTA2 results, and you have these 3 files: LC 2023, LC conf 2023, and LC pval 2023. So for the land cover map, actually, it's the first file, just called LC. It's followed by the time period where you want the corresponding as the time period you selected for the land cover map. So here is 2023. The bottom left coordinates in pseudo Mercator coordinates reference system. The top right coordinates in the same coordinate system, and then the production date, so where the map has been produced. So, and you have the land cover map with 11 land cover types. You have a second product, which is a pixel validity map with the same naming, which corresponds to the number of dates that has been used in the time series in order to create the map. For example, if there are 10 Sentinel-2 image, then and there are clouds and other things. For example, you'll have between 0 and 10 dates available for each pixel. So when you have high values means that you have a lot of dates available, and then a lot of dates have been used in the classification. When it's close to 0, meaning that there are none has been used in the classification. And then the confusion matrix, which is just a PNG file, not a DVC PNG, which gives the accuracy score for each class of the map. So it's really interesting and provides a useful insight on which of the classification occurred and if everything was all right. So for the question about the cross-validation, it's produced taking a subsample of the reference data we give in input, meaning that not every data is used for the classification. So here it's an example of the land cover map over Luzon, and that we can open it. We have everything here in IOTA2 results. So you use land cover here, drag and drop. And we will also open the pixel validity map that we drag and drop. So we are back into QGIS. And to look at the land cover map, we can change the style by properties, style, load style, and then we can load the style from the IOTA2 results. So there are map style, land cover map styles, and the pixel val style. So we use the land cover map. So you can see now an example of the output. So that's the land cover map, and we have the pixel val. So we can do the same thing. Load the style created for this. Okay. So in this part of Batten, why do you think that, and little poll for you, why do you think there are less value on this part of the image instead of the rest? What can cause this, in your opinion? So here corresponds to the number of valid value of valid Sentinel-2 value used in the classification. So darkest area corresponds to the low number, and yellow area correspond to a high number of image. Alors, let some time to people to answer. So I don't know, Carla, for the open question, how to display the results, because we cannot display it. When we click on more, we cannot see the response. You know, or you can do a screenshot in 1 or 2 minutes to see if there are some interesting answers. Okay, so in this particular case, you know, if answer no. So in this particular case, actually, indeed it's a mountain that is located here. When you look at the Bing data, you see the mountain, but it's most because of the clouds that are just being on the in higher altitudes. There are more clouds in these areas than in the plains. So that's why there are less data around the mountain. And then thing here, it's something we saw that in the plain there are less clouds than around the mountains. But you can see other artifacts as well. For example, the MGRS grid doesn't correspond to the track of the satellite. So you can have several paths on the same track, and see here you can see that there are more data on this part of the tile than in this part, and it corresponds to the overlay of several different tracks here. So there are more data in this part than in the rest of the image. And you can see that it can explain a little bit the difference. It will explain a little bit the difference in the accuracy of the land cover, because here, for example, we have a lot of closed forest which was not detected, which was not present in 2020 in the NAMREA land cover map. So either there was a big increase in closed forests, either there is overclassification of this class. When we as we told earlier, there are some visual interpretation of the land cover and visual estimation of the accuracy of the land cover, but there are other validation metrics such as the overall accuracy, for example, precision recall F1 score and kappa. And we use in the data set, in particular, the kappa and the overall accuracy to have some algorithm here that explain the differences of each of these metrics. But you have everything plotted in a confusion matrix. So the idea here, it's which classes in this. So you can see here the confusion matrix with all values corresponding to all classes that has been used as reference here, and how everything has been classified in our process. And so we can see the accordance in the classification between the classified values and the reference values. We see that we have a kappa of 0.69 and overall accuracy of 0.74. And so we see that there are some confusion in some classes. Can you tell me what are the classes that are most confused each other? So two classes that are really confused in this example. Yeah, in this example, can you give me the two most confused classes that are present in this example? Then we can comment. Yeah, I see that some people start to answer. Yeah. So yeah, you're right. That's closed and open forests that are really confused. As we saw earlier, there are a lot of part of open forest that has been classified of open forest that has been classified as closed forest. So probably due to the problem we show earlier, so few data and in these areas. But there are also some confusion between fish ponds and marshland, for example, and brush shrubs and closed forests. There are some confusion as well in some other classes. Perennial crops, which consist of banana, mangoes, are really confused with the area of brush shrubs and forest. And there are some confusion between BTUP and open barren, so which is quite frequent because there is really low NDVI. So that's it for the presentation of the results. Do you have any question? You want something? Do you have more question about this part of the presentation? If there are no more questions, maybe we can close the session for today.
Etienne, so if everyone wants to ask a question, so just just drop them on the chat box below. Otherwise, so again, to everyone, thanks for your participation. So today we saw a lot of maps and we get a lot of engagement with our participants. So that's really, really appreciate it. And also the questions, like, thank you very much. So just like a few words from our side. So all the materials will be uploaded on the CopPhil Digital Campus. So the slides will be there. And then if you want to revisit some of the instructions from Etienne today, you can expect the recording in a few days. So it will be
there
there.
Is a question, Carla, actually.
Yes.
Apparently there is a question, but more from your side regarding the process of getting a certificate of attendance.
Yes, sure. So it's also via this platform. So there's just let me check. Give me a second. So let me open this. So just showing you now the CopPhil Digital Campus platform. So you just need to log in with your registered account and then browse through the courses and then so basically learn the course. So this also counts as learning the course. So you'll find the information here. The slides are already here. And then the steps and then the recording will be added. And then we just have a few items here. So the feedback form, the quiz, and then you'll have your certificate. So for the certificate, you just have to fill in a short feedback form. So just a few 6 questions about the day session, and then 3-item quiz. So it gave you some quiz items, so they're not that very hard. So we really hope you fill this in, and then the certificate will be automatically emailed to your account. So yeah, that's the step to get the certificates. And going back here. So again, thank you for your participation. So today we really learned like from the scratch. So we've shown how to visualize the Earth observation data sets. So from Sentinel-1 and Sentinel-2, we also created our own reference data sets, and then also like a run through of the whole CopPhil Land cover platform and the whole workflow for that. And also important and not should not be neglected would be the accuracy assessment of our results and how to improve them. If you have further questions, you can contact us. The materials will be on the CopPhil Digital uh, campus, and then these are the contact details of Marion and Isyan. So with that, thank you very much to everyone, and have a good afternoon, and see you all in the next training, and we'll keep you updated. Thank you very much.